So we're living in a world of just massive, massive data sets. How on earth do we find the best possible solution when there are countless options to choose from? Okay, let's dive right into that. It's honestly one of the biggest challenges in data analysis today, and the answer, maybe surprisingly, lies in methods that cleverly use a bit of randomness to hunt for those answers. So today, we're going to explore this really fascinating world of stochastic search. We'll start with the core problem itself, then look at two major approaches, one inspired by physics, the other by biology. Then we'll see just how far we can push these ideas, and most importantly, why they're so incredibly powerful.
Okay, so what exactly is the problem we're trying to solve here?
Well, imagine this. You're trying to find the absolute highest peak in a gigantic, fog-covered mountain range. You can't see everything. A simple approach might be to just keep walking uphill, right? But what happens is you'll get to a local peak, a pretty good spot, and you'll be stuck. You can't see the true global highest point through the fog, and every direction from where you are is downhill. That's the classic optimization problem.
So to solve that, we need a smarter way to search. And that's where stochastic search methods come in. They introduce randomness, which allows the search to, every now and then, take a step downhill. It feels wrong, but it's what lets you get out of that local peak and go explore other parts of the landscape. It's that touch of randomness that keeps the whole process from getting stuck.
Interesting. So can you give me an example of one of these methods?
Absolutely. One of the most classic examples is simulated annealing. And the best way to think about it is to picture a blacksmith forging a sword. To make the metal as strong as possible, they heat it way up and then cool it down really, really slowly. That slow cooling process lets all the molecules settle into a perfect, low-energy, highly ordered structure. And that is its optimal state.
So, this process is all about a key parameter, temperature. At the very beginning, when the temperature is high, the algorithm is actually pretty likely to accept a worse solution. This allows it to make these bold jumps and escape those local optima we talked about. But as the system cools down, it gets more and more selective, zeroing in on a really great solution, just like those molecules in the cooling metal.
Okay, so that's inspired by physics. Are there other approaches from different fields?
Oh yeah, and this is where it gets really, really exciting. Let's shift over to an approach inspired by biology. Now, instead of one single solution climbing a hill, evolutionary algorithms work with a whole population of solutions at once, and they mimic Darwinian evolution. It's not about one individual finding the best path anymore. It's about an entire species adapting over generations.
The whole idea here is a continuous loop of improvement. You start with a whole bunch of different solutions, and in each generation, you basically apply survival of the fittest. The best solutions get selected to be parents, and they pass on their successful traits to the next generation. It's this constant cycle of selection and variation that pushes the entire population toward an optimal solution over time.
And this whole process has a really powerful balance. On one hand, you have mutation. This drives exploration by injecting brand new, totally random ideas into the mix, letting you search the whole landscape. On the other hand, you have recombination, or crossover, which drives exploitation by intelligently mixing and refining the best ideas we've already found. You absolutely need both to succeed.
Now, this evolutionary idea includes a few specific methods. Two of the big ones are evolution strategies, which are fantastic for optimizing continuous numbers. Like fine-tuning the parameters in an engineering design. Then there are genetic algorithms, which are famous for that powerful crossover operator. That makes them great for solving problems where you need to mix and match different discrete parts to find the best combination.
Wait a second. You're telling me we can evolve solutions, but can we evolve entire programs?
Exactly. That's the huge leap that genetic programming makes. Instead of evolving simple strings of numbers, we're evolving the programs themselves, usually represented as these branching tree structures. So don't think of it as a collection of answers. Think of it as a population of competing computer programs, each one trying to be the best at solving a given task.
So the old evolutionary operators get adapted for this new program structure. Crossover, for example, becomes unbelievably powerful. It works by grabbing a random branch, a whole subtree of logic, from one parent program and just swapping it with a random branch from another parent. This creates a brand new child program that automatically blends the functions and logic of its parents. It's wild.
So what's the key takeaway from all of this? The big takeaway here is that these methods let us solve problems that are just way too complex for any traditional approach. When the number of possible solutions is astronomical, you simply can't check every single one. So instead, we use these incredible techniques inspired by nature to intelligently explore that vast landscape of possibilities. We're talking about everything from designing more efficient engineering components to automatically discovering new scientific models from data. These techniques are fundamentally changing how we find the best solutions.
Hey, if you found this explanation helpful, please consider giving it a like, sharing it with someone, and subscribing. It really helps us continue to break down these complex topics for you.
And it really leaves us with a fascinating thought. What new frontiers are we going to be able to explore when our problem-solving tools can literally evolve all on their own? Thanks for watching.